Looking at this view of Earth from space, it's easy to take the precise balance of our reality for granted. Gravity anchors us to the ground, atoms combine to build the biology of our bodies, and light travels across the vacuum of space to warm our planet. This exact arrangement makes human existence possible. But if we rewind the clock 13.8 billion years, all of that disappears. There was no matter, no light, and no space. Even time itself did not exist. There was only an absolute empty void. The physical laws, fundamental forces, and raw materials that build our reality locked into place during a single, violent second. To understand how our existence is even possible, we have to look past the stars and galaxies of the modern era. We have to dissect the chaotic, microscopic transformations that occurred inside the very first second of the cosmos. At a fraction of a second after the beginning, the entire observable universe was packed into a space trillions of times smaller than a single proton. In this hyperdense, boiling quantum state, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were melted together into a single, unified rulebook. The heat of this primordial era was so intense that the numbers lose their meaning to the human brain. To recreate even a tiny fraction of these energies today, we have to build massive, multi-billion-dollar machines, like the Large Hadron Collider here at CERN, just to smash individual particles together at near light speed. Under that original crushing density, the newborn universe was on the verge of collapsing back in on itself. Cosmic inflation prevented this. In less than a trillionth of a second, the fabric of space doubled in size roughly 90 times. This hyper-fast expansion is what actually put the bang in the Big Bang. It provided the sheer physical scale and the empty canvas required for a universe to exist without destroying itself under its own weight. As the cosmos exponentially inflated, its temperature began to drop. That single, unified force shattered, splitting apart to form the distinct laws of physics we experience today. This created a severe paradox. The newly formed particles flying through this expanding space possessed absolutely zero mass. Because they were weightless, they shot around at the speed of light, making it impossible for them to slow down and bind together into physical structures. The activation of the Higgs field introduced an invisible energy grid across expanding space. As those fast-moving particles zipped across the cosmos, they crashed into this thick, viscous field. This physical drag effect granted particles their mass. As they pushed through the resistance, their velocity dropped, allowing them to finally catch up and interact with one another. Without the drag of the Higgs field acting as a cosmic brake, matter could never clump together. The universe would have remained a blur of racing energy, entirely empty of solid objects. With particles now slowed and possessing mass, the cooling universe began spontaneously churning out matter. But for every single particle of normal matter created, an antimatter twin was also born. These pairs were bound by a strict rule. Whenever matter and antimatter touch, they instantly annihilate each other. This turned the early universe into a microscopic war zone, with particles constantly sparking into existence, only to destroy themselves in flashes of pure energy. Yet a tiny mathematical anomaly tipped the scales. For reasons physicists are still trying to figure out, the production was skewed. For every 1 billion antimatter particles generated, there was exactly one extra particle of normal matter. As the annihilations cleared the battlefield, that single, isolated survivor was left behind. A moment of wonder. Look around you. Every star in the sky, every planet in our solar system, and the biological cells in your own body are constructed entirely from that leftover debris. We are the surviving remnants of a microscopic war of annihilation. Finally, the clock crosses the 1-second mark. The ambient temperature of the universe drops to a mere 10 billion degrees. It is just cool enough for the surviving subatomic fragments, called quarks, to permanently lock together into stable protons and neutrons. If we fast forward 380,000 years, the environment cools even further. Fast-moving electrons slow down enough to be captured by the gravitational pull of those nuclei, dropping into orbit to form the universe's very first stable atoms. Before this, the cosmos was a thick, opaque fog of loose electrical charges that trapped light in place. The formation of neutral atoms suddenly cleared that fog, allowing the very first light to escape and travel freely through space. We can still detect that ancient glow today. In 1964, astronomers Arno Penzias and Robert Wilson used this instrument to capture the radio hiss of the cosmic microwave background. Our capacity to gaze back at those early cosmic structures has only grown. We continue to build increasingly complex tools, like the golden mirrors of the James Webb Space Telescope, to intercept that primordial light and map the initial architecture of our reality. Every physical law, every fundamental force, and every material ingredient governing our reality was negotiated and locked in during that first chaotic second. It laid the exact foundation needed for 13.8 billion years of cosmic evolution to